Hello everyone, my name is Rivera. Today I will be presenting a critical review of a scholarly article titled A New Threat Level Speculative Automatic Parallelization and Library Based on Duplicate Code Execution. The study, authored by Martínez et al., introduced an innovative speculative parallelization model and the speclib library designed to address challenges in multi-core processing. This presentation contains four chapters: introduction, analysis, evaluation, and conclusion. This is the details of the papers. Next, we will talk about the context and relevance. Why it matters? Because we want to improve slow single core in a multi-core system and also tackle the manual parallelization complexity. The key techniques is speculative execution and also validation and recovery mechanism. Next, we will talk about the significance of the output of this paper, which is a spec library. The significance of speclib. So highlights speclib simplifies dependency checking with the comparative performance on irregular groups, portable and easy to use. As we can see that in the sample code, the implementation of speculative parallelization is out of the box. It removes the dependency check-in, so it won't be tedious job and error prone. This paper makes three major contributions. First, it introduced a novel threat-level speculative model by duplicating execution. The second, it implements with the C++ library speclib. And the last one, it focuses on usability and performance. As you can see in the diagram is the parallelization diagram, and the bottom one is the sample of the speclib configuration and speclib execution function. Speclib has several strengths. It is simple to use and highly portable, relying on C++14 standard features. The lock-free strategy ensures high scalability while the use of thread pools avoid the overhead of frequent thread creation and destruction. Together, these features make Speclib a robust tool for real-world application. Despite its strengths, Speclib has several limitations. First is the cap of the speed up. Theoretically, its speed up is capped at half of the number of cores. The second one is the memory overhead from duplicating data is significant, especially for large datasets. Additionally, failed speculation can introduce performance penalties. This challenge highlights area for future research. The key results. The results demonstrate that speculative achieve up to 20 times speed up in benchmarks with high speculative success rates. For example, in the R-test reduction benchmark, careful parameter tuning enables SpeedLib to outperform Atlas significantly. However, this performance for benchmark with frequent dependency violations like 2D disk hosts was less impressive, highlights the challenge of speculative failures. Next, we talk about the feature enhancement. So, this library can be enhanced by adding helper classes for arrays and containers. The second one, it can be improved by adding techniques for distributed memory implementations. The last one, we can add enhancement to reduce the energy consumption optimization. I can see that as for the parallel speed up and superlinear in this graphic, we can also implement the enhancement here. The critical reflections. Observation from this paper, it has high potential for real-world application, but it has challenges in manual tuning, and of course, it has opportunity for hybrid mode by duplicate and selective checking. The benchmark used here is in this table and also its system configuration. Conclusion. Specly introduced innovative TLS for multiple core processor and it achieved high performance but with some trade-offs. This paper paves the way for future research in speculative parallelization. That's all for this critical review. Thank you very much.